It is Tuesday, February 17th, 2026. If you could zoom in, and I mean way, way into the molecular level of your own body right now, what would you actually see? We like to think of biology as this perfectly oiled machine, a symphony of precise interactions. But if you look closely, especially as we get older, it starts to look a bit less like a symphony and more like, well, like static.
That's a great way to put it. It's the difference between a pristine digital signal and, say, a radio that's just slightly off station. You can still hear the music, but there's this underlying hiss that just gets louder and louder over time.
Exactly. And today we are diving into two massive pieces of research that just dropped this week, and they paint two very, very different pictures of our biological future. On one side, you have the architects.
Right.
The tech giants at Isomorphic Labs just released a report on their new AI, IsoDDE. They're claiming they've basically built a God mode for designing drugs with atomic precision.
It is a huge leap. I mean, we're talking about engineering molecules that can manipulate biology in ways we couldn't even properly simulate a year ago. It's the ultimate tool for order and design.
But then on the other side, you have the entropy, a fascinating and, frankly, a slightly terrifying paper accepted by Nature Communications this month. It looks at what's actually happening inside us, and it turns out our internal operating system is accumulating noise glitches, errors, in a way we didn't fully understand until now.
It really is a collision of two worlds. We're getting exponentially better at building the keys, the drugs, just as we're discovering that the locks, our own bodies, are sort of rusting and changing shape in these chaotic, unpredictable ways.
It's the architect versus the entropy. That's how I'm framing this deep dive. So our mission today is to connect these dots. We're going to look at how IsoDDE is rewriting the rules of drug discovery, and then we'll pivot to this concept of DNA methylation instability, to understand the chaos it's trying to fix.
And definitely stick around for the end, because when you put these two ideas together, the implication for how we treat aging, not just disease, but the aging process itself, is pretty mind-bending.
So let's start with the shiny new toy, the architect. Isomorphic Labs released this report, February 10th, about IsoDDE, the Isomorphic Labs drug design engine. Now, for anyone who follows this space, the immediate question is, how is this different from AlphaFold? We spent all of 2024 talking about AlphaFold 3.
Right, so AlphaFold 3 was the revolution. It solved the protein folding problem. You give it a sequence of amino acids, and it tells you what the 3D structure looks like. It gave us the map of the territory.
But having a map of the territory isn't the same as, building a house there.
Precisely. AlphaFold is great at prediction, telling you what nature already built. IsoDDE is about design, telling you what we should build to interact with it. The bottleneck in drug discovery has always been something called generalization.
Okay, break that down. Generalization in what context?
Think about how AI learns. In the older models, if you asked them to design a drug for a protein that looked like something they'd seen before, in their training data, they were great. They could basically copy and paste the logic.
But if you threw them a curveball...
Exactly. A protein with a weird shape or a drug molecule with a structure that doesn't exist in nature, they just fell apart. They couldn't generalize their knowledge to the unknown.
And in drug discovery, the unknown is usually where the cure is hiding.
It is. If we only look where the streetlights are, where we already have data, we miss half the city. IsoDDE claims to have smashed this bottleneck.
And there was a specific stat in the report that jumped out at you, the runs and poses benchmark.
Runs and poses. It sounds like a Guns N' Roses cover band, doesn't it?
I was thinking a very intense yoga class.
Yeah, that too. But it's actually a really rigorous stress test for computational chemistry. It measures how accurately the AI can predict the pose of a drug molecule. Basically, how it orients itself when it lands on a protein. Does it park the car in the garage, front first or back first? And does it scrape the paint?
So how did IsoDDE do?
On the hardest subset of this test, where the chemistry is totally novel, stuff the AI has never seen, IsoDDE didn't just inch past AlphaFold 3.
No.
It more than doubled the accuracy.
Doubled. In AI development, we usually pop champagne for a 5% improvement.
Doubling is a generational leap. It suggests that the model isn't just memorizing, it actually sort of understands the physics of interaction. And the reason it's so much better is because it has mastered a concept called induced fit.
Okay, induced fit. I remember that from biochemistry class. Help us visualize that.
So the old textbook model of biology was lock and key. The lock, the protein, is rigid. The key, the drug, is rigid. They either click or they don't.
Simple. clean.
And completely wrong. Biology is squishy, it's wet, it moves. A much better analogy is a hand grabbing a memory foam ball.
Okay, I'm with you.
When the drug grabs the ball, the protein, the ball changes shape. It indents, it conforms to your fingers. The pocket for the drug doesn't really exist until the drug creates it by squeezing.
So the target is moving because you're hitting it.
Correct. And modeling that interaction, predicting how a protein will deform to accommodate a drug that doesn't exist yet, is incredibly, incredibly difficult computationally. That's what IsoDDE does.
The report mentions a specific example of this, right? Structure 8EA6.
Yes, 8EA6. It's a classic example of a cryptic pocket.
Cryptic pocket.
Mm.
Sounds mysterious. Like a secret level in a video game.
It basically is. In its natural state, this protein looks completely smooth. There's nowhere for a drug to land. AlphaFold 3 looks at it and says, undruggable, nothing to see here, move along.
Right.
But IsoDDE correctly predicted that if you bring a specific molecule close to it, the protein shifts. It opens a secret door, a cryptic pocket, and the drug just slots right in.
That's wild. So it's finding secret rooms in our biology that we didn't even know existed.
And that is the game changer. Because undruggable targets are usually undruggable because we can't see a place to put the drug. If IsoDDE can find these induced pockets, it unlocks a massive amount of disease targets we gave up on years ago.
But it's not just for small molecules, is it? The report makes a big deal about biologics, antibodies.
A huge deal. Antibodies are the heavy artillery of medicine, things like Keytruda or Humira. But designing them is a nightmare because of their structure. They have these long, flexible loops, the CDR loops, that have to grab onto an antigen.
I imagine long, flexible loops are hard to model because they could just flop around in a million different directions.
Exactly. They're floppy. Predicting where a floppy loop will be is chaos. But IsoDDE is reporting it's 2.3 times more accurate than AlphaFold 3 at predicting these interfaces. And compared to the other big competitor, Boltz 2.
I saw that chart. It wasn't even close.
It's something like 19.8 times better in the high accuracy regime for novel antibodies.
Hey, nearly 20 times better. That sounds almost like a data error. How is that gap so wide?
It comes back to that training on the unknown. Boltz 2 and others, they rely heavily on homology, looking for things that resemble what they already know. IsoDDE seems to have actually cracked the physics of the interaction itself, so it doesn't need a cheat sheet. It effectively unlocks a design space for antibodies that was just invisible to other computers.
There's one more metric here I want to touch on before we switch gears. Binding affinity.
Ah, the holy grail.
Why is this the holy grail? If we know it fits, isn't that enough?
No, fitting is only step one. You need to know grip strength. If a drug binds too loosely, it just washes away before it does its job. If it binds too tightly, it might never let go, or it might bind to other things it shouldn't and cause toxicity.
So it's the difference between a handshake and a death grip.
Exactly. And traditionally, to get that number, the binding affinity, you have to run these incredibly expensive, slow physics simulations called FEP plus OUP. It takes massive supercomputer time. IsoDDE claims to beat these gold standard physics methods, but it does it in a fraction of the time.
So practically speaking, this means a pharmaceutical company can test, what, 1 billion designs in the cloud, know exactly how tight the grip is for each one, and only synthesize the top 10.
It bridges the gap between the screen and the test tube. It de-risks the entire process.
Okay, so that's the architect. We were getting terrifyingly good at designing the key. But now we need to look at the lock, because while Isomorphic Labs is perfecting precision, this paper in Nature Communications suggests our bodies are drifting into chaos.
This is the pivot. We need to stop thinking about engineering and start thinking about, well, thermodynamics, entropy, disorder.
The paper focuses on DNA methylation instability, or DMI. But before we get to the instability, we have to establish what stable even looks like. They talk about ESLs.
Right, epigenetically stable loci. The researchers looked at the blood of over 1,600 healthy 18-year-olds.
Why 18-year-olds?
Because biologically, that's peak performance. It's young, pristine biology. And they found about 31,000 specific spots in the DNA CPG sites that were incredibly boring.
And in science, boring usually means reliable.
Exactly. In these young, healthy people, these 31,000 spots were quiet. They were unmethylated. Think of it like a freshly paved, clean highway. No potholes, no debris, just a smooth surface.
And then they look to what happens when we get sick or just get older.
And that's where they found the mess. They introduced this metric, DMI. If the ESL is the clean highway, DMI is when someone starts dumping trash, these methylation tags, all over the road.
So methylation, which usually acts as a switch to turn genes on or off, is just appearing where it shouldn't be.
It's appearing randomly. It's just noise. And this noise correlates with some very bad outcomes. They looked at thousands of patients with blood cancers, leukemia, AML, CLL. The level of this instability, this trash on the highway, it just skyrocketed.
Okay, but here's the chicken and egg question. Does the cancer cause the mess, or does the mess cause the cancer?
That is the big question. But look at the longitudinal data. When a patient goes into remission, when the cancer is clinically gone, the DMI levels drop. The highway gets cleaned up.
That sounds like good news. It suggests the body can repair itself.
It is, until the patient relapses. When the cancer comes back, the DMI spikes again. But, and this gave me chills when I read it, it doesn't just spike randomly. In many cases, the exact same spots become unstable again.
Wait, so the body, it remembers the specific pattern of chaos.
They call it epigenetic memory, or the zombie effect. Even when the cancer is undetectable by standard tests, there is a scar or a memory of that instability just waiting to reemerge. The entropy follows a path.
That's terrifying. It suggests that remission isn't a clean slate at all. The seeds are still there.
It implies that DMI could be a much more sensitive radar for disease than anything we currently use. It's tracking the software glitches before the hardware actually breaks.
But this paper wasn't just about cancer, and I think this is where our listeners really need to lean in, because this affects everyone.
Yeah.
They found this instability in people who don't have cancer.
Yes. This is the broader implication for aging. They analyzed data from the Framingham Heart Study, a massive decades-long data set. And they looked at people who were, by all standard accounts, healthy. High levels of DMI, high levels of this random noise in the blood correlated significantly with cardiovascular disease and coronary heart disease.
Heart attacks.
Yes. And here is the kicker. This risk was independent of genetic mutations.
Explain that distinction, because we're always told our genes are our destiny.
Usually when we talk about heart risk or cancer risk, we look for mutations. CHIP mutations, for example, broken hardware. But this study showed you can have perfect hardware, pristine genes, no family history. But if your epigenetics are messy, if your software is glitchy, your risk still goes up.
So you can have a brand new computer, but if the operating system is full of bugs, it's still going to crash.
That is the perfect analogy. And the data shows that even in healthy donors, DMI just creeps up with age. We are all slowly accumulating this noise. It is a universal clock of biological entropy.
So let's bring these two worlds together. On one hand, we have IsoDDE, the architect, giving us control. On the other, we have DMI, the entropy, showing us how we lose control. But we need to get mechanistic here. Why is DMI bad? What is actually breaking when these sticky notes land on the clean highway?
The paper digs into this, and it's fascinating. They found that this instability tends to happen in very specific places. Gene promoters.
The landing strips for gene activation.
Right. The promoter is where the machinery lands to turn a gene on, and that machinery involves proteins called transcription factors.
So if the landing strip is covered in debris,
The pilot, the transcription factor, can't land. Or worse, it lands in the wrong spot. The paper specifically mentions a gene called PRDM5.
PRDM5, what's its job?
It's a tumor suppressor. It's a brake line for cancer. You want that gene working. But in these patients, the PRDM5 promoter gets cluttered with methylation. The switch gets jammed.
So a brake line is cut.
Exactly. Another one is RGS2, which is linked to hypertension and heart health. When DMI spikes, the regulation of these critical genes just fails.
And they identify the specific pilot that gets blocked, right? KLF12.
Yes, KLF12. It's a transcription factor that needs a clean sequence to bind. When you have DMI, KLF12 can't bind properly, so the control circuitry of the cell starts firing all these incorrect signals.
Okay, so here is the billion-dollar synthesis. We have IsoDDE. It's an engine designed to create molecules that can bind to anything, even cryptic pockets or these difficult interfaces. Could we use the architect to fix the entropy?
Theoretically, yes. And this is where the industry is heading. If we know that DMI is jamming the landing strip for the RGS2 gene, and that's causing heart disease.
Could we use IsoDDE to design a molecule that binds to that jammed landing strip and just clears it off?
Yeah.
Or maybe a molecule that mimics the signal that's being lost?
We could. IsoDDE allows us to target protein-DNA interactions in ways we couldn't before. If DMI is the check engine light telling us the car is breaking down, IsoDDE gives us the wrench to actually go in and fix the specific part that's failing.
It feels like we're moving from an era of blunt force medicine, chemo, radiation, statins, to Debugging.
Debugging is exactly the right word. DMI gives us the error log. It tells us, hey, line 4000 in your genetic code is glitching. And IsoDDE gives us the ability to write a patch for that specific glitch.
But the challenge is the scale, surely. DMI isn't just one spot, it's systemic. It's happening everywhere.
It is. But the fact that we can now measure it, that we can quantify this noise, that's the first step. Imagine a future where you go for your annual checkup. They don't just check your cholesterol, they check your DMI score.
Sir, your entropy is a little high this year. Your software is getting buggy.
Exactly. We see instability in the promoters for your heart health genes. And then, because of tools like IsoDDE, they prescribe a custom-designed molecule, maybe a biologic, maybe a small molecule, that stabilizes those specific regions.
That is hopeful, but it's overwhelming. It changes the very definition of healthy.
It does. We are looking at the raw data of life and death here. One paper shows us how fragile we are, how the noise accumulates until the system crashes. The other paper shows us how powerful we've become, how we can manipulate the building blocks of that system with atomic precision.
It's a race, the architect versus the entropy.
And for the first time in history, the architect might actually have a fighting chance.
So let's wrap this up. We've covered a lot of ground. We have IsoDDE, the new engine from Isomorphic labs that double the accuracy of drug design, finds hidden pockets, and masters the handshake of molecular binding.
And we have DMI, the new thermometer for biological chaos, showing us how epigenetic noise accumulates with age, drives cancer relapse, and predicts heart disease, even in people with perfect genes.
We are standing at the intersection of these two discoveries. We can see the chaos, and we are finally building the tools to tame it.
It's a pivotal moment. February 2026 might be looked back upon as the week we stopped just guessing at biology and started truly engineering it.
Which brings us to our final thought. We always like to leave you with something to chew on.
Here's what I'm thinking. If DMI is essentially a measure of the accumulation of noise in our biological software, a measure of entropy, and IsoDDE allows us to rewrite biological interactions with perfect precision, are we moving toward a future where we don't just treat disease, but we actively debug the entropy of aging itself?
If aging is just code rot, maybe we finally have the text editor to fix it.
It's a big if, but the tools are finally on the table.
A fascinating week for the future of our own bodies. Thanks for joining us on this deep dive. We'll see you next time.